So the purpose of today's lab is that we want to essentially prove the validity of what we've been working on for the past week. F net equals m times a, and it's also the vector sum of all forces. Okay? And we're going to do that using a pulley system with a cart and some masses hanging over the edge. Don't show any hustle or anything. Okay. All right. So the system is going to be just like this. You're going to have one of the wooden tracks. You're going to have a pulley that's going to be attached to this little piece of meter stick that's sticking out from the end. Okay. You're going to run a string over that pulley. There will be masses hanging from that string, and the other end of the string will be attached to your cart. The best place to attach that string, okay, is on the front end of the cart, on this or this, okay, either spot. On the top or the bottom, there's a little loop, plastic loop, for you to run a string through and just tie a knot. Okay, I would suggest that probably the bottom loop, okay, it probably won't matter, but the bottom loop might be a little bit better than the top loop, just because there's going to be some torsional force, okay, that could cause the cart to move slightly. Okay, all right. So that's where you tie on the string. Now, the other part of this is that we're going to have some mass on the cart as well. The reason for that is we don't want to change the mass of the system. In case you're looking at variables, we want the mass of the system to remain the same throughout all of the trials. What we're going to change throughout the lab is where that mass is located. By changing where it's located, we're going to change the applied force. Yeah, you're going to watch this again and get all this, right? Yeah, that's why I'm doing it. Okay, that's why I do this. All right, so we're going to be changing the applied force, and what we're going to be measuring, okay, recording, is the acceleration of the cart. So we're testing what is the effect of varied applied forces on acceleration for Newton's second law. Okay. Some things we want to make sure don't change throughout the lab. We already said one, mass of the system. Okay. We also want to make sure, as best we can, that our system is level. The best way to do that is to open the Level app on your phone, set your phone on the track, and adjust accordingly to make the track as close to level as humanly possible. Okay? And then everything else, we're not changing tracks in the middle or anything like that, because then that might alter how much friction would be involved in the system. We want that number to stay around the same. All other conditions to do with the movement of the cart should remain the same. Okay? Because all of them could affect the acceleration of the cart, and that's the thing we're monitoring, is the acceleration of the cart. All right, so there, we've covered most of the design now. Okay. For our hypothesis, okay, so we want to generate a hypothesis that is a tentative answer to this problem. What relationship exists between the applied force, okay, and its acceleration? So I would say that the if part of your hypothesis should be some kind of restatement of Newton's second law. So if Newton's second law says blah, 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 okay, the and part just describes the experiment, okay? A system will be accelerated by varied applied forces, okay, while acceleration is measured, well, something like that, okay? Then predict what will happen as the applied force increases. Right, so this is a pretty simple hypothesis. Okay, you're telling me what Newton's second law is, and then basically saying that again as your prediction. Okay, like, you're going to have to word it carefully so it doesn't sound like you're saying exactly the same thing twice. Okay, so as we're doing this, obviously you have to have one member of your group that's got the SparkView app still on their phone, hopefully, or can reinstall it quickly, because that is how you will be getting the acceleration of the cart. So you're going to be making a velocity versus time graph, right, of the 4 trials, right? And all you need from that velocity versus time graph is the slope of each line, okay? Because the slope of the line on a velocity time graph is acceleration, all right? So I did this lab, and this is the data that I got, okay? So trial 1 is the blue dots, trial 2 is the red dots, trial 3 is the yellow dots, trial 4 is the green dots. I got obviously an increasing rate of acceleration each time, and I can read that acceleration directly off my legend if I say use equation in there just like we did for all the other labs, all right? So you're just going to build a velocity versus time graph, okay? Get your 4 trials on there. The slope of the line on each trial is your acceleration, and you can see I definitely got an increasing rate of acceleration for mine, and you'll get similar to that. All right, so the lab will work like this. We're going to have our setup. It doesn't look exactly like this, but it looks essentially like this. We'll have the cart. Okay, the cart has all the sensors in it, so you don't need this thing back here. Okay, we don't use those anymore because now it's all in the cart. Okay, in the cart will be some masses. Right? Because like we said, we want to keep the mass of the system the same. Right? We want essentially the total mass of the system to be, I think it's 400. No. So our total mass is going to be 670 grams, or 0.670. No, 0.720. Okay. So 0.720 is going to be the mass of our system. Okay, unless you have a red cart, and then it's going to be 724 grams. Because for some reason, the red carts are 4 grams heavier than the blue carts. Don't ask me why. Mr. Dickey and I measured them multiple times in case we were crazy. And we weren't crazy. Well, we're crazy, but not about this. Okay, just know that, okay, our total mass of the system is going to be 720 grams. Okay, so you're going to have, in the first trial, you're going to have the cart, which is 274 grams if it's a red cart, and you're going to have 400 more grams on the cart. Okay, so each group is going to get a set of masses. Okay, and what you're going to do is take 400 grams and stick them in the cart. Now, you can't just stick them in the cart like this, because if we do that, and then we let go of the system and the string pulls on the cart, Newton's first law will apply. And what will happen? The cart will slide out from under the masses, because the masses will try to stay put because of their inertia. So, we need to make sure they stick to the cart, which is why there's a little bit of sticky tack up here on the whiteboard. Okay, just take a little bit of it, okay, and put some on the bottom of each mass and stick it on the cart. Okay, that'll be enough to keep it from moving during the experiment. You don't need a lot. Okay, now they don't move. Okay, that'll be enough for what we do. Okay, so I'll have the cart plus 400 grams, and I'll have 50 grams hanging over the pulley. Okay, everybody with me so far? That'll be my first trial. So how this will work then is this is going to require multiple people. Okay, you can't just set it up and hope that it'll work. Okay, all by yourself. So you're going to have the cart attached by the string, and you're going to have the 50 kilogram mass, or 50 gram mass, hanging over the pulley. And I should have tied this on before, but I didn't. All right. Now, you have to watch the length of your string. Here's why. As the mass falls off of the pulley, it's only going to apply a force for how long? Exactly. It's only going to apply a force until the other mass hits the ground. So if you make this string really long and the mass can only fall this far before it hits the ground, you're not going to get very much data. Okay? So what you want to do is make it even probably a little bit better than this so that the mass is just below the pulley when your cart is at the back of the track. Okay? So then what you're going to do is you're going to hang the mass. So for this first trial, there's my 50 grams. Okay? And this is how you start it. Okay? Somebody holds the cart from the back of the ramp, and then when the person with the spark view presses the start button and they start seeing the data, let it go. Now, I'm only one person. In this group, there would be another person at the other end of the track. Why? To catch the cart. If you don't, it will Dukes of Hazzard off the end of the ramp and destroy itself on the ground, and then I will be displeased. Okay, so we don't want that. All right, but for this first one, the acceleration is pretty slow. Okay, and I mean, the mass hits the ground before I get to the end of the ramp, which is good. That means I got the string length about right. Okay. Then for the next trial, you're going to transfer 50 grams off the cart over the pulley. 50 grams each trial. All right, so obviously that means I don't just take this mass and put it over there, because that would be another 200 grams. So I got to take this one off, okay, and probably do a little altering. Maybe I put 100 grams over this and put 50 back on here. Okay, we're transferring just 50. So you got to do a little bit of math, like permutations and combinations, but you don't actually have to show your work. Okay, just 50 grams moves from the carts to the pulley each of the 4 trials. Nick?
Is the sticky tab involved in the total mass?
We're going to say that it doesn't play a factor.
Okay.
Yeah, you're right. But then we'd have to pull out the scales and everybody would have to measure this amount of sticky tack weighs less than a gram. So it's not, we're going to say it's within experimental error. Yeah. Maybe it's a source of error. But since it is staying the same every single time, it really doesn't affect the experiment. Okay? That's why we can kind of do it that way. All right. So that's what you're going to do, 4 trials, okay? And you can see we got the numbers already up here on the chart, so you just kind of have to follow that, okay? We're transferring 50 grams from the cart to the pulley for each of the 4 trials. You have to be mindful as you start increasing the amount of mass that's over the pulley, because this thing accelerates hard on the last 2, okay? Because you got a lot more mass over the pulley than you got behind it, okay? And these things can get moving. All right, let's get our data. And then I'll talk some more. Otherwise, you'll forget everything I say. You probably already forgot most of what I said. So, okay, let's just get the lab set up and do that. Okay, start with 200 grams on, 50 grams over the pulley. Transfer 50 grams each time. Then we'll talk again. Okay. Once you have the data, okay, you need to build your Google Sheet. Okay, building your Google Sheet means that all you have to do is have the time for run 1, because it'll be the longest, okay? The time for run 1 and the velocity data for all 4 runs. Okay, so first column would be time for run 1, and then you'll have velocity run 1, velocity run 2, velocity run 3, velocity run 4. All right, you are probably going to have to trim all of those because you're going to have those parts where it was flat. Okay, take those parts where it was flat off. Okay, so you only have the part where it was actually accelerating on your graph. Okay, so when that graph is built, it should look like that one I showed you a minute ago, right here. Okay, so your data, okay, would end up looking like this. Okay, so you'll have your time from run 1, your velocity run 1 data. Okay. Velocity run 2 data, run 3, run 4, okay? And then you'll have your graph. Once you build it, it'll be a velocity versus time graph, and it should look something like that, okay? And you can see that I don't have any of the flat parts on there anymore. I've taken them off, okay? Once you have that, then you can move on to the analysis part of this. Okay, so analysis question number 1, build the graph. Okay, that's all you're doing for analysis question number 1, is getting that velocity versus time graph and getting the slopes on the, or getting the equations on there so you have the slopes. Okay, question number 2, calculate the applied force and record it in your table. Okay, so the applied force tells you how to do it right here. Take the hanging mass, so just the mass that's hanging over the pulley, and multiply by 9.81. We're using gravity as our applied force. All right, so that one's a pretty easy calculation to make. Okay, the acceleration, this you just take from your graph. Okay, so the slope of the line for each one of the trials, put it in the box. Okay, and then the net force. So take the acceleration of the system, this box here, okay, so whatever this one was, and multiply it, okay, by the mass of the system, which in every case is how much? 720, or if you had a red cart, 724 grams. But it needs to be in kilograms. So it'll be 0.720 or 0.724, depending on whether you had a red or a blue cart. Okay, so you're just taking the mass of the system and multiplying by that. So it'll be 0.720 times whatever this number is, and then same thing in this column, 0.720 times whatever that was, okay, and so on. That's all you're doing to fill in the chart. Okay? All right. Using the formula described in the background information, calculate the force. So that's actually what we did here. That's the net force. Okay, so that was what I just showed you. And then what is the relationship between net force and acceleration? Well, what is it going to be? As the net force goes up, what happens to the acceleration? You're just putting that in words for me. Okay, a couple sentences describe what's happening there. Okay, number 5, draw a free body diagram to describe the forces involved. Now, here's what we have to consider. Okay, this question number 6 is going to be necessary for you to do question number 5. What you're going to find here is that the net force and the applied force are not equal. Okay? In a perfect physical world, they would be. But here they're not. And you have to figure out why. But there are 2 different scenarios. You may only have one of them, or you may have both of them in some of your, like one in one trial and one in another trial. Here are the 2 scenarios. You may end up with, okay, a situation where the net force was actually greater than the applied force. Okay, so if you found that the net force was greater than the applied force, that means there wasn't just this force. Something else was also pulling the cart forward, not just the hanging mass. Okay, that does happen. It's the less common of the 2, but it does happen. You have to try and figure out what that other force might be. Okay, and again, think about some of the things we checked before we started. Okay, the other situation is that the applied force will be greater than F net. That's the more common situation. That means that something is pulling which way? If this force is greater than the net force, then something is pulling back. Okay? And there's a couple of options for what that force might be. Okay? And it's probably a combination of both of those forces, but you'll have to figure out what they are. Okay? So that's how you would answer 6 and 5. So you kind of got to figure out this part for 6 so you know what forces to put on your free body diagram for question number 5. Okay? Everybody with me there? So this is the part that requires you to do a little bit of thinking. Okay? Look at what situation you have. Is your net force bigger than your applied force? Is your net force smaller than your applied force? And figure out why, what other forces might have been involved. Okay? Then conclusion, same as always. Copy and paste your hypothesis and tell me, does your data support what you said in the hypothesis? And then 2 sources of error. Okay? We made some assumptions in this lab. They might not be true. They may have affected the lab slightly. Right, so you got to talk about those. Questions there? All right, so you got a bit of work to do, okay? Because getting the data took a little longer than I anticipated. But that's okay. We still had time, so you've got all the data you need. If you're struggling anything with Google Sheets or something like that, just let me know and I can give you a hand.